what we're going to start looking at today is sequences where, or series where the terms are not all positive. So we've been talking about ones where you add up a bunch of positive terms, and we've also been talking specifically about ones where most of the function types are the same. So like it's all power functions or all exponential functions, maybe a few with trig mixed in or something, but they boil down to P series or geometric series. We're still going to be dealing with those, but we're going to be looking at ones like this. So we're going to be looking at something like the sum -1 to the k over k from k equals 1 to infinity. And I want to just kind of talk about in general how that series differs from this series, which is very similar in appearance. So if you were to, so what we're going to write right now is just kind of the idea of this stuff. It's not what you would do as a proof. But if you look at the series on the bottom, that is the series 1 plus a half plus a third plus a fourth plus a fifth plus a sixth and so on. Does that make sense to everybody? And so you have that series. And what does that series do? The one on the bottom half of the screen. Does it converge or diverge?
Diverges.
Yeah, it diverges. This is the harmonic series. And so we talked a while ago, it's about why the harmonic series diverges, but it does, it goes to infinity. And so we've got that series. Now, the series on the top is what's called an alternating series. And so if I start plugging in values of k, -1 to the first is -1. And so we get -1 over 1 for the first term. And then when I plug in 2, -1 squared is +1. So I get +1/2. And if I plug in 3, I get -1/3 because -1 to the third is -1. And so we get -1 over 3. And if I plug in 4, I get +1/4, and then -1/5, and +1/6, and so on. So -1/7, +1/8. And the idea is that most of the time, when you have -1 to the k, most of the time that's going to be an alternating series. And what we mean by an alternating series is one where the terms that you are adding alternate from positive to negative or from negative to positive. And it's every other term where one's negative and then a positive and then a negative and then a positive and so on. In general, we're going to be talking about series that have just some negative terms, but this series is what's called the alternating harmonic series. And it turns out that it converges, but we'll kind of see why later. But just thinking about it, if this diverges because it goes to infinity, why it's not obvious that this would converge, but why maybe would that be possible for this to converge even though this diverges? Why is it possible this would converge here? What do you guys think? Why logically, when you change it from this to this, could it go from infinity to a finite number? Any ideas?
Oh, because in the alternating one, you're adding and subtracting both.
Yeah, half the terms are negative, so you're subtracting half of them. And so you're doing adding and subtracting. So regardless of whether this is infinity or not, this is for sure a lot smaller than that. And now maybe it's just slower to go to infinity. It turns out this one's not. But if half of them are negative, this is a lot smaller than this one. Does everybody get that idea? Everybody clear? Okay, so what I want to talk about in general, so we'll explain later why this one converges, but it's good to know that this one does converge. But what I want to talk about in general is if you have a series AK, where, okay, AK is just some term in this series. AK is the sequence that we're adding up. Maybe it's all positive, maybe it's all negative, maybe it's alternating, or maybe it's just randomly positive, randomly negative. I want to talk about that compared to its absolute value. And so we can think of that in reference to what we were just talking about. So what if we were talking about the sum -1 to the k over k, and then we're talking about the sum of the absolute value of -1 to the k over k? What happens when you take the absolute value? So like back up here, these are the two series we're talking about. Um, this is that top series. When I take the absolute value of all the terms, it becomes this one. Does everybody see that? Okay, so the absolute value of that is 1, the sum 1 over k. And I didn't put the k equals 1 to infinity, but assuming it's going from what k equals 1 to infinity, this is this top series. This is the harmonic series. And so what happens is the absolute value makes all the negative terms positive. So in general, what happens when you take the absolute value is if this is already all positive. So if AK is like the ones we've been talking about so far, and these are all positive, what happens when you take the absolute value?
Won't change.
It doesn't change. So if this is already all positive, when you take the absolute value, it doesn't change at all. If this is all negative, then this just becomes all positive. Does that make sense? And this is, if this is sum of both, then okay, this gets bigger. So we're not going to prove this, but logically then, if you think that we could say that we know this converges, so when you make it bigger, then that's not what happened up here, right? The absolute value did not converge. But if you make it all bigger and it converges, what do you think would have to happen here? So like, first of all, okay, if this is all positive, this is the same series. Does that make sense? So if this is all positive, it's the same series, meaning, okay, that converges. Now, if it's all negative, then okay, this one's bigger, but -1 times this one would also converge. What if it's alternating? So if half of them are positive, half of them are negative, and when you take the absolute value, that converges. What do you think happens when you go back and make half of them negative again? What would be the logical conclusion?
Would it also converge?
Yeah, it would also converge, because if anything, you've made it bigger. You may not have changed it when you take the absolute value, but if there are negative terms here, you've made them all positive. So the logical idea is that it would then converge. And the proof's a little more complicated than that, but that's a good way to think about it. So the idea is that if the absolute value converges, then the original series converges. That is a theorem that we call the absolute convergence theorem. And what it says is if the infinite sum, so k equals whatever, 0 we'll say, to infinity, of the absolute value of AK converges, then the sum k equals 0 to infinity of AK converges. And we'll use that a good bit. Okay, but that idea gets us into a new term for convergent series. So we can talk about these two series, AK and the absolute value of AK, and then the term for AK. Okay, and so this is a weird chart because we're putting the same column twice, but we're going to describe it two different ways. If this one converges and its absolute value converges, then what we say is that that original series converges absolutely. That means the series itself converges and the absolute value of the series converges. Why does that mean that pretty much all the ones that we've been doing this week If they converge, then they converge absolutely. What types of series have we been working on so far this week?
All positive.
All positive. And so if this is all positive, this is the same series. So if this converged, the absolute value automatically did. So it was automatically absolutely convergent, or you could say it converges absolutely because the absolute value was the same series we were dealing with anyway. That's why when you look at series 3, the directions mention this, and it didn't change the way you do any of those problems, even though we didn't really talk about this until now. We talked a little bit, somebody asked at the end of class yesterday, we talked a little bit about it, but that's why what we're doing on those series so far this week proved that they converged absolutely because they were all positive. So parts of those proofs where they were all positive, that means the absolute value is the same thing. Does that make sense? Okay, now it's also possible like this one. So here we've said this converges, but its absolute value diverges, right? So the absolute value of the alternating harmonic series is the regular harmonic series. Well, here the series itself converges, but its absolute value diverges. So this series converges, but we describe that as converging conditionally, meaning the series does converge, but if you take its absolute value, then it no longer converges. It makes it so big that it goes to infinity. So if the original series converges and the absolute value diverges, we say that the original series converges conditionally. And now it still converges, but what we're saying though is that the series does not, the absolute value of the series does not converge. That, except for maybe a couple of the telescoping ones we were dealing with earlier, but so that's different. But for the ones that we've been doing, for the most part, all of them have been all positive terms, and so then none of them would have done this because the absolute value is the same. A couple of the telescoping ones would have been converged conditionally. So like we proved that some of those telescoping ones converged, their absolute values, a lot of those would have diverged if you took the absolute value. And so maybe those did. But aside from that, none of the ones we've been looking at would have converged conditionally. Does that make sense? Everybody clear so far? Okay, and then I'm going to put these two up. So if this diverges and this converges, and this diverges and this diverges, one of those combinations is actually impossible. So I want you to not say it yet, but think about which one of those is possible based, which of those is not possible based on what I've got on the screen. Okay, so which one is not possible? Somebody tell me.
Wouldn't it be diverges and converges?
Yeah, this third one, this row is not possible. Why is this not possible?
Because if that one goes to infinity, then its absolute value would have to go to infinity too, right?
Yeah, and that's back to this absolute convergence theorem. Yes, you were right. So if the absolute value converges, then what do we know about the original series? So if the absolute value converges, the original series has to converge. So it's not possible. That's what this theorem says. Does that make sense? Everybody clear? Okay, so this is not possible, which means we don't give a new description for diverges. We still just say it diverges. If the series diverges, then its absolute value automatically diverges. Does that make sense? Everybody clear? Okay, so we're giving new terms, converge absolutely, converge conditionally. And so now the directions, which they already said on series 3, just to kind of get you used to that, but the directions for problems are now going to say show or prove whether the series converges absolutely, converges conditionally, or diverges. All right, so we're going to start with this one. The sum from k equals 3 to infinity of -1 to the k over k to the fifth. And so if we do that, because we're trying to figure out whether it converges absolutely or converges conditionally, we're almost always, when we deal with alternating series, we're almost always going to start by looking at the absolute value first. Does that make sense? Okay, so we don't want to imply that we think this is equal to its absolute value. It's not. And we're not really comparing it to its absolute value. We're not doing a comparison. We're just going to say, okay, we don't like dealing with this, so I want to deal with the absolute value. So the word I use is consider the sum of the absolute value of -1 to the k over k to the fifth. So when you're writing an explanation of this, that's a good word because it's just saying, okay, we're going to think about this one instead. We're not saying we're doing a comparison. We're not trying to prove it's bigger or smaller or any of that. We're for sure not saying this equals this. It's not equal to that. And so we just say, okay, consider this other one. Okay, well, what is the absolute value of that? What happens if you take the absolute value of -1 to any power? What's the absolute value of -1 to any power?
Wouldn't it just be 1?
It'd be just 1 because it's always -1 to a power is always either 1 or -1. So the absolute value of both of those is 1. So the absolute value, that's 1. And then what's the absolute value of k to the fifth? K to the fifth, because as k goes to infinity, k is positive. So then the absolute value is 1 over k to the fifth, of the sum 1 over k to the fifth. Does that make sense? Okay, now we're going to show what this one does. What's it do? Does it converge or diverge? Ignore the original one, just the one in blue. What's this one do?
Converges.
It converges. Yeah. So we say this converges, and we give an explanation as to why. This converges because it's a p series where p is equal to 5, and what's significant about that is that it's bigger than 1. Does that make sense? Okay, now we have just proven that its absolute value converges. So does this theorem that we've talked about tell us what happens to the original or not? So the absolute value converges. What does this say then happens?
The original converges.
The original converges. So we go back over to the original, say, so the original series, the sum of -1 to the k over k to the fifth, that also converges. Does it converge conditionally or converges absolutely? Does it converge conditionally or converge absolutely?
Absolutely.
Absolutely, because its absolute value does. And so it converges absolutely, which is kind of the answer to the question. So we'll box that in or circle that. So it converges absolutely by the absolute convergence theorem. And it's a little bit weird because it sounds like the rationale is the same as the answer, and it kind of is. But the name of that theorem is also pretty close to the way you say the answer. So it converges absolutely by the absolute convergence theorem. Does that make sense to everybody? Pretty easy. Any questions so far? Okay. Number 2, same directions. All right, so we're going to start same way. So it's an alternating series pretty much every time when we're dealing with an alternating series. We're going to start with its absolute value. There are a few exceptions later, but normally we're going to do this. So we're going to say, okay, consider the sum of the absolute value -1 to the k over k. Well, that's the sum of 1 over k. Does that make sense? All right, what does that do? Converge or diverge?
Diverges.
That diverges. And we give a rationale for that. We can say it's because it's the harmonic series. Or we could say it's a P series where P is equal to 1, which is less than or equal to 1. Either way, it diverges. Now, what does this theorem say? So it says if the absolute value converges, then the series itself converges. What does it say happens when the absolute value diverges?
Nothing.
It says nothing about that. So when this happens, that's unfortunate because the absolute convergence theorem doesn't tell us anything. But what this does mean is that which of these answers has to be wrong based on this. It cannot do which of these. It cannot converge absolutely. It could converge conditionally, which I already said it did. We're not done showing that, but it could converge conditionally, or it could diverge at this stage. Does that make sense? Everybody clear? Okay, so we're going to come back and finish this problem in a minute, but I want to talk about what's called the alternating series test next, and I'm going to squeeze that in up here. And so the alternating series test says this. Okay, so if the sum of AK, and we can put bounds on this, but we'll say K equals 0 to infinity, but does not have to start at 0. If that is equal to -1 to the K times BK, meaning it's an alternating series, you've got, it's really like AK includes the -1 to the K, BK does not. And 3 conditions hold. BK is positive. The limit as K approaches infinity of BK is 0. And BK is decreasing. Then the sum K equals 0 to infinity of AK converges. Okay, so this is what the alternating series test says. That's a pretty formal statement of it, but the textbook would have a very formal statement of it. I think it's exactly the same as this, although I did not look right before this. So this is what our alternating series test says. So AK could be basically anything, but in practice, it's going to have a -1 to the K, and it's got to be able to be written this way. The BK positive guarantees it's actually alternating. So like you're taking a positive number and then multiplying by 1, -1, 1, -1. If BK weren't positive, then this might not actually be alternating. Does that make sense to everybody? I see what I'm saying? Okay, and then you have these other 2 conditions that BK has to go to 0 and BK has to be decreasing. And so we're going to go through those. If those things are true, so if it's really alternating, the limit of BK is 0 and BK is decreasing, then the alternating series AK converges. It does not say BK converges, but AK does. And so there are 3 conditions to show. First, BK is greater than 0. Second, the limit of BK is 0. And third, BK is decreasing. If those 3 things are true, then the series, the alternating series, converges. So we're going to go back down and do that on this problem. So we've already said the absolute value diverges. Then, okay, BK is what based on what the alternating series test said. So BK is like, AK is the whole thing, and the whole thing is equal to -1 to the K times BK. So what would BK be here? What do you guys think?
1 over k.
Yeah, it'd be 1 over k. So bk is 1 over k. And now we're going to show those three things. So the first thing is bk is positive. Well, you don't have to explain that much, but you need to say it, and then you need to be right about it. So how do I know for sure that 1 over k is greater than 0 on this problem? Because k is going from 1 to infinity, so you have 1 divided by a positive number, so that's for sure positive. Does that make sense? Okay, so that's positive. The second thing is the limit as k approaches infinity of bk of 1 over k is 0. This one is pretty straightforward, that 1 over infinity is obviously going to go to 0. And the third thing is that bk is decreasing, and that's the one that a lot of times takes a little bit of work to show. This is on a video from a couple weeks ago where we're talking about monotonic sequences. And if you go watch that video again, I go through 3 different ways to show that a sequence is decreasing. When you're talking about bk here being this simple, 1 over k, the quickest way to do that is to look at bk plus 1. Well, that's 1 over k plus 1. So b sub k plus 1 means plug in k plus 1 for k, and compare that to bk. Well, 1 over k plus 1 is less than 1 over k because the numerators are the same, but the denominator here is bigger and everything's positive. So this is saying that the term, so bk is a random term, bk plus 1 is the term after that. The term after it is always smaller than the term before it. That means that it's decreasing. Does that make sense to everybody? Now, this proof is more involved if this formula is harder, but we show all 3 of these things. If all 3 of those things are true, then the original series, the sum -1 to the k over k, converges. Does it converge conditionally or converge absolutely? What does it do here?
Conditionally.
Yeah, it converges conditionally because we already proved its absolute value diverges. So it converges conditionally by the alternating series test. All right, any questions on that? Let's follow it. Everybody good? Okay. I'm going to put 2 problems on the screen, and I'm going to give you a couple minutes, and I want you to go through the proofs of these. So we're going to do problem 3 and 4. So again, the directions are show whether the, we'll copy this real quick. Show whether the series converges absolutely, converges conditionally, or diverges. And it'll let me paste it in. Then, okay, perfect. And now number 3 is going to be the sum k equals 1 to infinity of -1 to the k over the cube root of k. And number 4 is going to be the sum k equals 1 to infinity of -1 to the k over k to the 7th. All right, so I'm going to give you guys about 2 minutes to work on that just because the video will drag otherwise. But try that, and then we'll work on it here together in just a minute. Okay, so we're going to start working them together. If you think you're good, keep working and kind of check versus what I do. So on both of these, we should start by comparing to, I'm sorry, considering, and the words don't matter a whole lot, whether you say compare to or consider, but we're not really doing a comparison. So we're considering the sum, and then I'm just going to write the absolute value of AK. And kind of the understood thing on these proofs is if you use AK, I'll assume that's the original series unless you tell me otherwise. So if you want to use the symbol AK, I assume it's the original problem. Or if you want to say AK is something else, that's fine. But if you don't tell me, then we'll make that assumption. And then that's going to be 1 over the cube root of K, which is the same thing as 1 over K to the 1/3 power. That diverges because it's a P series where P is 1/3, which is less than 1. That tells us that the original series does not converge absolutely, but it could converge conditionally or it could diverge. So we go to the alternating series test. So we say, okay, well, BK is the non-alternating part of that. That's 1 over the cube root of K. 3 things to show. One is that that is positive. So 1 over the cube root of K is greater than 0. Not much to explain there as long as we're correct. The limit as K approaches infinity of 1 over the cube root of K is 0. Again, that's pretty clear because it's 1 over infinity. And the third thing, which is a little bit more involved, is BK is decreasing. And this one, though, is a relatively simple formula. So we can do that just by comparing BK plus 1 and BK. So it's 1 over the cube root of K plus 1. That's smaller than 1 over the cube root of K, which is BK. So the next term is always smaller than the one before it. Man, that does not look like a K, but the next term is always smaller than the one before it, which is the definition of decreasing. And so then this series converges conditionally. By the alternating series test. And so there's kind of 2 parts to this proof. So you do the P series over here first, and then you go back and do the alternating series test to show that it converges conditionally. Does everybody follow that? Any questions on that one? Okay. And so then problem 2, we're going to go over here and say, okay, consider the sum of the absolute value of AK. That's the sum 1 over K to the 7th. That converges because it's a P series where P is 7, which is bigger than 1. Now we go back and we don't need to do the alternating series test. We can just say, so the original series converges absolutely by the absolute convergence theorem. That says absolute convergence theorem. Let's make that a little bit neater. But that is it on these 2. Questions on these? Everybody good so far? Okay, so the format of the proofs is the same. You get this easier series from the absolute value. and you prove what it does. If the absolute value converges, then the original series is very easy to prove because automatically by the absolute convergence theorem, the original series converges. If this diverges, this is more work, but as long as the alternating series test holds, then this converges, but it'll converge conditionally. You could go through the alternating series test on problem 4, but you don't need to. So if you did all this on problem 4, it would still converge, and it would converge absolutely because this one did, but there's no need to do this on problem 4 because once we know the absolute value converges, then we already know the original one converges. So there's no need to do the alternating series test. Does that make sense to everybody? It's clear what I mean? Okay, I want to look at one harder problem, maybe 2 harder problems. So let's look at number 5, same directions. Okay, so we're going to look at this. And now it's an alternating series. So we're going to start again by considering the absolute value. So we're going to come way over here. I'm sorry, no, we're not. We're going to go just over here a little bit. And we say, okay, consider the sum of the absolute value of AK. That's the sum K over K to the third plus 6K plus 7. Does that make sense to everybody? Okay, what is more complicated about this now than these? So what's harder? So this is not just a P series, right? So what would you do to show whether or not this series converges?
You would compare it to its biggest terms on top and bottom.
Right. So you now in turn say, okay, compare to the sum K over K to the third. Well, that's 1 over K squared. Does that make sense? Now we have 3 series going on. The one on the right, we're going to prove first. It converges. It converges because it's a P series where P is 2, which is bigger than 1. Does that make sense? Now we're going to go to this middle one. We're going to use a comparison test on that. Remember that comparison tests require everything to be positive, but it's the absolute value, so it's for sure all positive. On this problem, can I use the direct comparison? So this one converges. We would want the one we're comparing it to be smaller. Is this middle one smaller than the one on the right? It is, because the bottom is bigger and the top is the same. So I can use the direct comparison test. So I'm going to write K over K to the third plus 6K plus 7 is less than K over K to the third. That's true because the numerators are the same and the denominator of the one on the left is bigger than the denominator of the one on the right. It's K to the third and K to the third, but on this one we add 6K plus 7, meaning this is a larger denominator. For the logic in the comparison tests to work, everything has to be positive. So we also say, okay, it's greater than 0. So now this middle series, which is the absolute value, converges by direct comparison. Does that make sense? Everybody clear? Okay, now we're going to go back. So we've proven that the one on the right converges. We've proven the one in the middle converges. Now we're going to go back and do the original. Well, since the one in the middle, since its absolute value converged, then the original series, the sum AK converges, and it converges absolutely by the absolute convergence theorem. Does that make sense to everybody? Any questions? Okay, now we're going to do more examples of these, but what typically happens is that if it's an alternating series where the rest of it is all the same function type, so either all power or all exponential functions, then they follow this form where you usually have 3, not 2 parts. These up here had 2 parts because when we took the absolute value, we were already at a P series. Same thing with the first 2 we did. When we took the absolute value, we were already at a P series, and then it was quick to do the other part. In general, you have this 3-part thing where, okay, you have this middle one that's not as simple as a P series. And then you go to the one on the right and compare it to a P series. But in general, this might be a P series, or it could be geometric, because it could be exponentials. Whatever this does, if this one converges, then the middle one is going to converge. If this one diverges, the middle one is going to diverge. And it's going to be by either direct or limit comparison tests. So you're going to use one of the comparison tests, and which one you're using does not depend on the answer over here, converge, diverge. It depends on the relationship between the two. So like whether this is bigger or smaller and whether that's what you want or not. Or you could just default to limit comparison test. But the conclusion here, if this is converge, this is going to be converge. If this one diverges, this is going to be diverge. Does that make sense? And then when you go back over here, this is going to be absolute convergence theorem. If the middle one converged, it's going to be alternating series test. Usually, if the middle one diverges. There are some exceptions, and we're going to talk about exactly when they are tomorrow, but this is the format of these proofs. Because this is going to build so fast tomorrow, I want to show you the homework that you should go ahead and do before attending lecture tomorrow so that tomorrow is as helpful as it can be. So you need to practice this before we go in. And so series 4 is now what we're working on. And it looks like, man, I did not look at this, but apparently these are the 2 examples I just did in class. I would rework them. So, or if you want to change it from class, change that to a 6 and change this to like the 5th root of K or something, so that it works out to be the same basic thing, but I would rework them. 3 and 4 are pretty much the same. -1 to the K plus 5 still alternates. -1 to +1, -1 to the K minus 4 still does that as well. And so the first 4 we should do, and then you should try 5, 6, and 7, which may be a little bit of a stretch from what we've done today. We've done one like 5, but not like 6 or 7. But I would recommend that you try to do those 3 using my solutions to help, because tomorrow's going to make a lot more sense if you've tried this and kind of struggled through a couple of examples before you watch me do like 3 more. And so if you can, do the first 7 before tomorrow's lecture, or if you're watching the recorded lecture, try the first 7. The first 4 for sure are straightforward from what we've done today. 5 is just like the last one. 6 and 7 are a bit of a stretch, but use the solutions to help you, and then that'll make tomorrow's lecture make a lot more sense if you've tried to think about it first on your own, and then you're thinking about it with me, hopefully live tomorrow, but if not, when you're watching the video later. 8, 9, and 10 are just more examples, and those are the other ones that are going to be due Monday, but they'll be a lot easier after we've done tomorrow's lecture. So tomorrow we'll do a few more examples. We're going to talk about how to know what to do before you start. So like you should know the format of these proofs before you even start, but that'll, like I said, that's going to be a lot easier if you've tried these problems on your own first. So this is a really good cutoff for today. So go try the first 7 problems before tomorrow's lecture. If you have last minute questions, stick around. Otherwise, I will see you guys tomorrow. Thanks, you guys.